So a molecular orbital diagram summarizes how the molecular orbitals are related to the atomic orbitals. In other words, tells you where they come from. For example, here this molecular orbital called 1s sigma comes from a combination of the 1s orbitals on two atoms. This is for diatomic molecules. So this is a diagram, an orbital diagram for a diatomic molecule. In particular, a homonuclear diatomic molecule. Homonuclear means same two atoms, like H2 or He2 or Li2. Okay, so the 1s orbitals can combine to give you a bonding orbital, which would be lower in energy than either of the atomic orbitals, or they can also give you what's called an anti-bonding orbital. So 1s sigma star, the star in the label for the orbitals indicates anti-bonding. So the 1s sigma star, that's another molecular orbital which happens to have higher energy than the atomic orbitals that it came from, so that would be called an anti-bonding orbital. Okay, so a molecule that has lower energy than the contributing atomic orbitals are called bonding orbitals. Those that have higher energy are called anti-bonding orbitals. For diatomic molecules, names of molecular orbitals are given by the Greek letters sigma, pi, delta, and phi. It's analogous to S, P, D, and F for atoms. For molecules, we use sigma, pi, delta, and phi. In this particular case, in this diagram that we have here, this is a sigma. It's called the 1s sigma. This is 1s sigma star. This is 2s sigma. This is 2s sigma star. This is 2p sigma. So the labels tell you what atomic orbitals the molecular orbital came from. So when you say 2s sigma, that's a sigma orbital that's formed between the 2s orbitals. Okay, so this 2p sigma right here means that's a sigma orbital that's formed between two 2p orbitals. So if I have a 2pz orbital this way, okay, which is positive on this side, let's say, and negative on this side, and then another 2pz orbital in the other atom would be over here, positive and negative on the other side, and that gives me a bonding orbital. Okay, that's a sigma orbital between those two atoms. That's constructed from their 2pz orbitals. Now, in general, bonding orbitals are the ones that have the high electron density between, so you have constructive interference of the orbitals between the nuclei, whereas anti-bonding orbitals would give you a molecular orbital that has a node, we say a node. That means between the nuclei. A node simply means that the probability of finding electrons between the nuclei is small, so that makes the nuclei see each other better, you might say. So there will be a stronger repulsion, so that's why that's an anti-bonding situation. Okay. If you do an internet search for molecular orbitals, there's a lot of websites that you'll find will give you very nice images to help you visualize how molecular orbitals are constructed from atomic orbitals. So here's a search that I just did. One of the better ones to look at is the one, if you can find one from Purdue University, this one right here, chemed.chem.purdue.edu. So that particular link is pretty nice. Here it shows you how you can construct a bonding orbital from two 1s orbitals. Okay, so if you have a 1s on one atom and a 1s orbital from the other atom, let's call those atoms A and B, you get a sigma bonding orbital right here, sigma 1s. And if you do 1s minus from atom A minus 1s from atom B, then right here in between the nuclei you'll see destructive interference, so you get a node between them. Okay, so here's a diagram that results from that. Okay. Right here. So the bonding orbital would be lower in energy than the two atomic orbitals, and the anti-bonding orbital would be higher in energy. Okay, so that's the orbital diagram for that. And further down here, here's an illustration of how you can construct a sigma bonding orbital from two pz orbitals. So this is 2pz orbital for atom A, and it's a 2pz orbital for atom B. Okay, so if the positive lobes overlap, you get a bonding orbital. If this lobe was negative, okay, if this lobe was positive and this lobe was negative, you get an antibonding orbital, sigma antibonding orbital. So again, here you have a node in between the nuclei where there's a low electron density. Okay? And here down here you have a diagram that illustrates how you can get pi orbitals from a pair of 2px orbitals. So you have a 2px orbital on one atom and another 2px orbital from the other atom. So let's call this atom A and atom B. Okay, if they're both positive on the same side and negative on the same side, then you end up with a molecular orbital which is positive on one side and negative on the other side. And so that would be a pi bonding orbital. So, and if this was negative, okay, right here, then you would end up with a pi antibonding orbital. Now, pi orbitals generally come as a pair, okay, because you can construct a pi orbital using px orbitals and another pi orbital using py orbitals, and those will have the same energy, okay? And same thing with pi star orbitals. You can construct pi star orbitals from px or a couple of px orbitals and a pi star orbital from a couple of py orbitals.